Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. We hear the phrase, "We are stardust," so often it has become almost cliché. But what does it actually mean? It is not just poetry, it is hard cosmic chemistry. Every atom in your body, from the hydrogen in your water to the iron in your blood, has an origin story written in the fires of the universe. And for one crucial part of you, the very framework that holds you upright, that story is uniquely violent. Your skeleton is an inheritance from a supernova explosion. To understand this, we need a quick dive into human composition. We are mainly made of four light elements: oxygen, carbon, hydrogen, and nitrogen, making up about 96% of our mass. The remaining 4% includes trace elements and the structural components, most notably calcium and phosphorus, which are the primary building blocks of your bones. Where do these elements come from? The universe has two main factories, the Big Bang and stars. The Big Bang, the genesis event of the cosmos, was only capable of producing the lightest elements: hydrogen, H, helium, He, and trace amounts of lithium. Everything else, literally every other element on the periodic table, had to be forged later, inside stars. These elements are the core ingredients of chemistry, biology, and ultimately, human life. Stars are vast, sustained nuclear fusion reactors. For most of their long lives, stars like our Sun are busy converting hydrogen into helium. But when stars are significantly larger than the Sun, 8 times larger, or more, their internal pressure and temperature allow them to proceed through more complex cycles of fusion, known as stellar nucleosynthesis. They burn helium into carbon, then carbon into oxygen, oxygen into neon, and so on, building up layers like a cosmic onion. This fusion process is exothermic, meaning it releases energy, balancing the star's gravity and sustaining its structure. This element building continues until the star's core begins to produce iron, element number 26. Iron is the critical breaking point. Fusing atoms heavier than iron is an asterisk endothermic process. It consumes energy instead of releasing it. This sudden consumption of energy triggers an immediate and catastrophic gravitational collapse. The star, having run out of fuel to fight gravity, implodes in a fraction of a second, causing an enormous shockwave that violently reverses direction. This event is a Type II supernova. This is where your bones come in. Most of your carbon and oxygen were created relatively gently in the cores of large, but not necessarily doomed, stars. But the elements required for your skeleton, calcium and phosphorus, require the extreme conditions of that supernova event. Calcium, Ca, and phosphorus, P, are essential. Calcium phosphate forms the crystalline structure that gives bone its incredible hardness and rigidity. But these elements are not easily made in the calm core of a living star. They are created during a brief, hellish moment, the final seconds of the star's life, right before and during the supernova explosion itself. As the core violently collapses and then rebounds, the pressure and temperature reach absurd extremes. This shockwave blast provides the necessary energy to trigger rapid element formation, a process called explosive nucleosynthesis. It is in this environment, thousands of times hotter than the star's main sequence phase, that the star rapidly synthesizes elements in the mass range of silicon to nickel, including the huge quantities of calcium and phosphorus that are scattered across the galaxy. These newly minted heavy elements, the stellar shrapnel, are ejected at millions of miles per hour into interstellar space. They mix with clouds of pre-existing hydrogen and helium, forming the next generation of gas clouds. Our own solar system, including Earth and everything on it, formed from one such gas cloud that had been enriched by countless earlier supernova events. So, when you break down your skeleton's composition, you're looking at a cosmic time capsule. The hydrogen atoms floating around you are 13.8 billion-year-old Big Bang leftovers. But the calcium atoms locking together your bone structure are the direct, violent residue of a massive star that ended its life in a blaze of glory long before our sun was born. You carry the atomic signature of a stellar catastrophe. Our skeletons are the physical record of the universe's most dramatic recycling program, connecting us directly to the life cycle and fiery death of stars across the cosmos. For more incredible facts like this, don't forget to subscribe and turn on notifications.